Students, hi, this is Mr. Bob. In this video, we're going to talk about particle physics, and this is the second of a two-part video on particle physics. This one, we're going to talk about antiparticles and conservation laws. And again, before watching this video, you should have watched the particle physics part 1 video, and you should have also listened to the 13-minute podcast by the Radiolab group. The podcast overall is titled Desperately Seeking Symmetry, and you're only listening to that 13-minute segment within that hour podcast. It's called Nothing's the Antimatter is that subsection. And ideally, you would have set up focus notes in your journal. And again, you should, several days after taking these notes, go back and revisit them. Again, reminders, when you're taking these videos or doing these videos, avoid mindlessly copying, selectively write down what you hear. And for the sample problems, definitely pause and try and solve them on your own. If you're still confused, please mark points of confusion and follow up as necessary. 2 essential questions for this video. What are antiparticles? How do they differ from particles? And the second one is, what are the conservation laws for particle physics reactions? So let's talk about antiparticles. It's kind of hard to wrap your head around this, but our best knowledge, our best understanding suggests, and this is backed up by a mountain of evidence, experimental evidence, that every particle has an antiparticle which has the same mass but an opposite charge. So therefore, we know about protons, but there are also such things as called antiprotons, okay? And they have the same mass as a proton, but they have the opposite charge, -1, and we'll show that here in a little bit. Also, there are things that are very similar to electrons, but have the opposite charge. And sometimes you'll hear them called as anti-electrons, but more often than not, they're called positrons, okay? And this is usually how you see them written, E with a positive superscript by it. And we've already talked about that, right? When we did beta positive decay, we talked about a positron being emitted. That's an anti-electron. An important thing to note that'll make more sense to you later on in this video and as we proceed on is that other quantum numbers, including something called baryon number, lepton number, and strangeness, are opposite for antiparticles when you compare them to their particle cousin. Okay, and like the video, like the podcast, the Radiolab podcast talked about, these antiparticles first came up in mathematical equations that a guy named Paul Dirac was working with back in the 1920s. And it wasn't until several years later that they were proven to exist in the lab. But it kind of shows how oftentimes in physics, math leads the way before we have the experimental ability to kind of prove it. So let's talk more about each type of antiparticle. Quarks have antiparticles. So if you imagine, we talked about the 6 quarks. Up, down, charm, strange, top, and bottom. For every up quark, there's an anti-up quark, okay? Or for the down quarks, there's also a version of a down quark, which is very similar to it in its properties, but negatively charged, and that would be an anti-down quark. And oftentimes with quarks, the way we indicate that they are anti-quarks is we basically put a bar over the symbols. So if I want to show that I have an anti-up quark, I would just write U with a little bar up above it, like you see here. And I could also call it U bar, and that's actually the way it's actually said sometimes. So U bar is known as an anti-up quark. So let's do a couple practice problems really quickly. And again, I just want to emphasize, it's so important that you understand all the information in your data booklet for this section, because there's a mountain of it, and it just makes it so much more straightforward. So the first question is, what sort of charge will anti-quark U bar have? There should be a bar above there. That bar got moved. So if we look down here, notice we know an up quark would have a positive 2/3 charge, and we know that an anti-up quark is going to have the opposite charge of that. So charge on U bar equals -2/3 E. Okay, second question. The pion was the first meson to be discovered. It is composed of the following: U d bar. What is its charge? Well, let's go through it. We got the charge on U, a regular quark, is positive 2/3 E. And then a down would have a -1/3 E, but an anti-down would be the opposite of that. So this would be plus a -1/3 E, right? Which is a positive 1/3 E, which means that a meson has a charge of +1 E. Awesome. All right, leptons also have antiparticles. The leptons, if you recall, let's just kind of go review something really quickly. Leptons come in 3 flavors, so to speak: generation 1, generation 2, and generation 3. Generation 1, you have the electron, which normally we write as E with a minus above it. And then you have the muon in generation 2, which often is written as this, or it can also be written U minus. And then the third generation is the tau, which also can be a tau with a minus symbol above it. So, and they also have neutrinos, right? There's the electron neutrino, the muon neutrino, and the tau neutrino. A little different in terms, they have antiparticles too, and they follow the same idea, but a little different in this sense is that the antiparticles are most commonly designated with a positive symbol. And so, like I already mentioned this, the antiparticle for the electron is the positron, and you most normally see that written as E with a positive symbol. Okay? And again, I just want to emphasize, let's go over here and look at how the information for the leptons tells you right here, right? So you know, you don't have to memorize this. The charges on the leptons are all given to you. And you just have to know that if we're talking about the opposite, the antiparticle, it's going to have the opposite charge. Oh my gosh, the joke. Okay. What sound does a subatomic duck make? And it's not the sound of my dog barking in the background. A subatomic duck says, "Quark, quark." Haha. Okay, let's talk about the 4 conservation laws, okay? And my apologies, the dog's gonna bark for at least another 30, 45 seconds. Just try to ignore her. We have 4 conservation laws that all particle physics reactions have to obey. Charge, baryon number, lepton number by family, and strangeness. And I suspect some of you, at least, have been saying already or are saying right now, "Mr. Bob, this is all really odd. How do we know, how can we believe this? What evidence do we have to support this?" And I'm going to tell you that there is a mountain of evidence in particle physics, meaning reactions, particle physics, accelerator reactions in cyclotrons, Large Hadron Collider, other places across decades that support all of this information that I'm telling you. And it's really hard because it doesn't really encounter our everyday existence, right? We don't really encounter it on a daily basis like we do other physical laws. But there is a large amount of evidence that supports what we're talking about here in the standard model. Does this mean that it's totally settled? Absolutely not. Still exploring weird things. Still don't understand it all, but what I'm telling you here is pretty well established. Okay, so what I'm saying here is the reason we know these conservation laws generally hold is because we have yet to find reactions that disobey them, okay? If we do come up with reactions that disobey these laws, then we have to somehow amend the laws. So the first one we've already talked about, conservation of charge. In nuclear physics, we talked about how charge has to be conserved, like in beta minus decay, beta plus decay. And so that's true for all reactions, all particle physics reactions, okay? The electric charge, the total electric charge before the reaction starts with the particles involved has to equal the total charge after, okay? The next one is something called baryon number. So it turns out that quarks each have a baryon number. And so the total baryon number has to be conserved in a particle physics reaction. So if I count up all the baryon number and add it up to get a total baryon number before reaction, I have to have the same total baryon number afterwards. What is a baryon number, or what sort of baryon number do quarks have? Every quark has a baryon number of positive 1/3. And if we're talking about an anti-quark, it's going to have a baryon number of negative 1/3. Okay. Now, let's just do a practice problem with this. What is the baryon number of a proton? And what is the baryon number of an antiproton? And what is the baryon number of a meson? Okay. Well, proton, remember Pud Nud? Proton is going to be up, up, down, right? So if proton is up, up, down, notice we have positive 1/3, plus 1/3, plus 1/3, meaning a proton has a baryon number of 1. What about an antiproton? Well, antiproton is going to be, let me just fix this. It should be bar, bar, bar. So that would be negative 1/3 plus another negative 1/3 plus another negative 1/3, which gives you a baryon number of -1 for an antiproton. And then a meson has a quark makeup Q bar. Sorry, these got mixed up somehow. And so it's going to have a baryon number of a plus 1/3 from the quark and a negative 1/3 from the antiquark. And that's going to total up to be a total baryon number of 0 for a meson. Okay. I just want to emphasize again, if you're sitting there saying, wow, I'm going to have to memorize this. No, you're not. Look right here. The baryon number for all the quarks is given to you. And you just have to remember that if you're talking about an antiquark, it's going to be the opposite. Okay. Conservation of lepton number by generation. This is the third conservation law that particle physics reactions have to obey in order to be valid. So leptons have lepton numbers, which is similar to baryon numbers. So a lepton is going to have a lepton number of +1. An anti-lepton is going to have a lepton number of -1. And lepton number must be conserved by generation or family. So what I mean by that is, if you recall, we have Gen 1, Gen 2, and Generation 3. So Generation 1 is the electron, neutrino, and the electron. Generation 2 is the muon, neutrino, and the muon. Generation 3 is the tau, neutrino, and the tau. So when you explore whether a reaction is valid, you have to make sure that lepton number is conserved for Generation 1 and for Generation 2 and for Generation 3. Okay, so that we'll go through examples, and it'll make more sense when we go through some examples in another video. Okay, so with that in mind, let us talk about finally the last one, conservation of strangeness. Okay, so total strangeness, there's this quality that physicists observed occurring in reactions because they were longer lived than other reactions. Okay, so they came up with this quality called strangeness to account for it. So the total strangeness before a reaction happens has to equal total strangeness after, and the products of the reaction. And the strangest number of a hadron is 0 unless it has strange or anti-strange quarks. So, and here's where it's a little different. They don't call it strange for nothing. The strange quark is going to have a strangeness number of -1. Notice how this is a little different because all the other ones, the numbers were positive and then the anti ones were negative. This is reversed. The strange quark has a quark number of -1, and the anti-strange quark has a strangeness, of +1. And all other quarks have a strangeness of 0. And there is a key point. There's like a little asterisk here. You saw it up here. And I just want to emphasize that strangeness does not need to be conserved when strange particles decay through the weak interaction. Remember, the weak interaction is what's responsible for beta- decay and beta-positive decay. One of the best ways to tell if the weak force is involved, if you're not sure, is to see if there are leptons that appear in the products of the reaction. If leptons appear in the products of the reaction, there's a good chance that, that you have the weak force occurring there, and then you don't need to worry about strangeness. So I want to again emphasize that. Notice what I just talked about, leptons and lepton number 1 and -1, that's right here. And the last law, all quarks have a strangeness number of 0 except the strange quark that has a strangeness number of -1. Okay, this information is given to you in your data booklet, and you just need to know how to apply it. So hopefully with that, you understand a little better and you have an answer, at least a partial answer, the start of an answer to the questions of what are antiparticles, how do they differ from particles, and what are the conservation laws involved in particle physics. Thanks, everyone.